Okay, so boa tarde, good afternoon. It's a real pleasure to have today Professor Yara Jaffé speaking at the talk of Valongo Observatory. And she's gonna give a talk about galaxy evolution in dense environments. And Yara studied physics at the University Simón Bolívar in Caracas, Venezuela. And then she did her PhD in Nottingham, where I had the pleasure to meet her for the first time. Then she has been a postdoc at the Osservatorio Astronomico di Padova, INAF. And then she moved in Concepcion, where she worked as a postdoc at Universidad de Concepcion. And finally, she had her last postdoc as a ESO fellow in Santiago, and is now a professor at the Institutes of Physics and Astronomy of the University of Valparaiso. And it's gonna be a pleasure to listen to your talk, so I'm gonna go out now.
Thank you, Ariana, and thank you in general for having me in this talk. It's a pleasure to be virtually in Rio de Janeiro. I hope it was in presence, but hopefully that can happen soon. I'm going to just share my screen.
Yes.
Okay, so can you see my screen?
Not yet.
No?
Yeah, now yes. Now I'm gonna go out. Yeah.
I hope you can see the full screen. If not, please somebody interrupt and let me know.
Okay.
Sorry?
It's perfect.
Okay, great. So as Ariana said, I'm going to be talking today about galaxy evolution in dense environments, and in particular in something I've been working in the last years, which is to find galaxies in the moment of transformation. To understand how galaxies form and evolve, we want to catch galaxies in the moment in which they're transforming. So I'm going to talk about the specific case of jellyfish galaxies that you'll hear all about in a second. And the work that I'm going to present has been done in collaboration with many, many people, but mainly from the GASP and bodies teams. So to understand how galaxies form and evolve, which is what I'm interested in studying, it is very important to also understand how the environment of galaxies forms and evolves. So we know from our lambda CDM cosmological models that the universe forms hierarchically from the very early universe here at high redshift, so the box on the left. This is a cosmological simulation showing how the structures in the universe evolve with time and grow over time, forming these massive clusters that we see nowadays that continue to grow through the accretion of groups, filaments, isolated galaxies, and even from merging with other clusters. So we know that galaxy environment evolves over time, and in general, from the point of view of the galaxies, it means that the galaxy's environment gets denser as galaxies evolve. Okay, so a galaxy that was born in a relatively isolated environment at high redshift could have ended up being in a massive cluster at redshift 0. So that's something that we need to take into account, and we need to really understand what physics happens while galaxies migrate from one environment to the other. So in the last decades or even century, we've learned a lot about the populations of galaxies through observations. And I guess the most established observations of galaxies across environments is there is a very strong color bimodality. So we have very red and dead passive galaxies and blue star-forming gas-rich galaxies. And the distribution of these types of galaxies across different environments is very segregated. So there is a famous relation called the morphology density relation that tells us that in the very dense cores of these massive galaxy clusters, as I show here in the background, this is a cluster from a cosmological simulation. In the very dense regions, we find mostly big, massive elliptical and lenticular galaxies that are almost completely devoid of all gas from which to form new stars. And this is why we say that these galaxies are dead. They have very red colors, they're dominated by red wavelengths in their spectra, which means that they don't have current star formation going on. And if we look at galaxies in these very isolated environments or lower density environments, we are more likely to find gas-rich spirals. Okay, so this can be summarized by the two plots here on the left. Here I show what I mean by the color bimodality. So galaxies essentially split between a red sequence of passive galaxies and a blue cloud of gas-rich spirals and irregulars. And the middle panel shows the morphology density relation, which was established in the 80s and tells us that the fraction of spiral galaxies decreases dramatically as the density of galaxy increases. And this happens at the expense of the increase of the early type galaxy population. And by early type, I mean elliptical and S0 galaxies, which are galaxies that don't have the level of star formation that spirals and irregulars do. In addition of these two observations, we also know from the last few decades that by about redshift of 1 or 2, when the universe was kind of mid-age, this relationships started to be established. So if we look at clusters in the past, at redshift 1 or 2, we start seeing that the densest parts of the universe start to be dominated by these red and dead galaxies. And if we look at the evolution of the morphologies of galaxies with cosmic time, we see an impressive decline of the star-forming spiral and irregular population, as I show here on the right. Oops, sorry, my computer is very sensitive. And this decline is happening at the same time that the population, for example, of lenticular or S0 galaxies is increasing. So somehow we think that there is a transformation of galaxies that were originally formed as gas-rich spirals that somehow get quenched, the gas is consumed or removed, and they become these dead disk galaxies or even elliptical galaxies. But how exactly this transformation is happening, we don't know. We know it's happening. It definitely has to happen to explain the observed populations of galaxies, but we don't know exactly how it's happening. So, to begin to understand all the things that a galaxy can go through, we can essentially separate in two the main quenching mechanisms for galaxies. And I show here on the left a famous plot by Peng et al. In 2010, where they essentially show the fraction of quenched red galaxies across a range of galaxy mass and across a range of galaxy environment. And what we can clearly see here from a sample of many, many galaxies from the Sloan Digital Sky Survey is that both mass and environment are able to make red and dead galaxies. So if you go to the higher masses, you get that, above, let's say, 10 to the 11 solar masses for galaxies are essentially all dead. But if you look at the galaxies less massive than that threshold, it really depends where they live. I mean, if you see where they live, in which kind of density or environment they live, then you will know whether they're quenched or not. So we have a combination of what we call mass quenching and environmental quenching. So mass quenching can happen through internal mechanisms of the galaxies. And one of the most talked about ones is the feedback from AGN, so supermassive black holes at the centers of these galaxies that, through their feeding process create a lot of feedback. And then we have the environmental quenching, which is things that happen that affect the galaxy that have to do with their external environment of the galaxies. And this can be essentially summarized as the nature-nurture combination. So I'm going to focus on environmental quenching of galaxies, and I'm going to use this illustration by a dear collaborator of mine, Heidi Chung, who made this cartoon to show some of the things that can happen to galaxies in their lifetime. So in this cartoon, the stars in the galaxies are yellow, and the gas that the galaxy has within her is blue. So when you think of environment, the first thing you can think of is that galaxies can be close to other galaxies, and hence they interact with each other. So when galaxies merge, simulations and observations show us that a lot of the gas that the galaxies bring with them can be compacted, it can form a lot of new stars, you can have a burst of star formation, and then eventually you consume all that gas and you form a big, massive remaining galaxy. And this is one mechanism to form elliptical galaxies, for example. If you merge two spirals, you can form an elliptical. You can also have interactions between galaxies that don't actually merge, but they simply just pass by each other at very high speeds. And when you accumulate many of these high-speed encounters, you can remove a significant amount of mass from the galaxy, thicken the disk kinematically, and really distort it and transform it in a way. And this kind of behavior, this harassment, can happen to galaxies, for example, in massive groups or clusters, where the relative velocities of the galaxies are very high and they don't really manage to merge, but they just keep flying past each other. And then we have other mechanisms. So, for example, starvation is when you simply cut off the fuel of gas into the galaxy. So galaxies, it is thought that galaxies feed from gas from the large-scale structure, and then this gas cools and they can form stars. But if you stop this mechanism by putting a galaxy, for example, in a hot halo like a galaxy cluster, you essentially starve to death the galaxy. And if it doesn't have any more fuel to form more stars, it will just form the stars that had to form from the gas available and then starve to death. And another mechanism that I'm going to be talking a lot about today is called ram pressure stripping. And it has to do with the interaction between the cold gas in the galaxy and the hot gas in the cluster. So let me go into a bit more detail about this, since I'm going to spend the rest of the talk talking about ram pressure. So galaxy clusters, as you know, can be groups of hundreds or even thousands of galaxies. But galaxies actually account for only about 1% of the total mass in clusters. Most of the gas is, of course, in dark matter. And a small percentage of the gas is in this so-called intercluster medium, which is a very hot gas component that fills the space in between galaxies and that we can see in X-rays thanks to the thermal brainstorm emission. Okay, so when a galaxy is attracted by the big gravitational pull of a galaxy cluster and it falls into the cluster, it will feel a wind and a pressure, essentially, from this hot gas inside the cluster, in the intercluster medium. And this wind is able to strip or remove gas within the galaxy in the direction opposite to the wind. Okay, so here I show essentially the analytic, very simplified prescription of how ram pressure stripping can happen. This was published in a seminal paper by Gunn and Gott in the 70s. And essentially, when the ram pressure from the intercluster medium exceeds the galaxy's ability to keep its gas, which is essentially the anchoring force, stripping will occur. Okay, and this ram pressure depends on the density of this hot gas and the velocity at which the galaxy is falling through, while the anchoring force of the galaxy depends essentially on the mass profile of the disk, of how much gravitational pull this galaxy has to keep its gas. So there has been numerous simulations. Here's a very out-of-date list of some of the simulations of ram pressure stripping, and this is just one of many examples, just to show more or less what happens. So this is a wind simulation where you put, here on the left, you have a disk galaxy with a gaseous disk, here shown in green. And as time evolves, you have this wind that goes from left to right. And you see that the outer parts of the disk start to be stripped of gas, and you start forming these beautiful tails of stripped material that have these knots of denser gas. Okay, and simulations and also observations show that you can even form stars in these dense knots of stripped gas. Okay, but one interesting thing to look at here is that while the gas distribution of the galaxy is very disturbed, almost completely disturbed, the old stellar component in the disk remains pretty much the same. At least the old stars are unaffected, because this is This is a hydrodynamical interaction. It's not a gravitational interaction. Okay, so it essentially affects the gas, the collisional component. And in terms of observations, perhaps the most striking observations of ram pressure stripping at play come from radio H1 observations of galaxies in clusters. And that historically, the most beautiful examples are here next door in the Virgo cluster. So here on the left, I show a map of H1 imaging in galaxies around the Virgo cluster by the VIVA survey. Okay, this is Chung et al. 2019. This is the same woman that did the cartoons I showed you before. And as you can see, the intercluster medium emission from the Virgo cluster is here shown in yellow. So you have a very dense core, and then it gets less dense. It has a bit of inhomogeneities. And then the gas in the galaxies is shown here in different colors. And the galaxies have been magnified by a factor of 10 just so that we can see them. But you can see that outside the cluster, so in the outskirts of the cluster, we have much larger H1 disks than in the center. And if we go and look in detail at the morphologies of the H1 gas in these galaxies, you have what I show here on the right, that really impressively shows how the stellar disk in these galaxies, as seen by the optical images in the background, is pretty disk-like, undisturbed. But the H1 contours, which are the white ones, are clearly affected only on one side, showing that very likely sort of a wind is creating this one-sided asymmetry. So this is supporting evidence for ram pressure stripping. There have been many other studies, including our own. I'm going to talk about things that I've been directly involved with. So one of them were the deepest H1 observations done to that date. This was a few years ago now, with the body survey, so blind, ultra-deep, distant H1 environmental survey, where we looked for H1 in two clusters at around redshift of 0.2 and the large-scale structure around them. So this was the cool thing about it, that we have a really large field of view to look at gas in these clusters. And one of the things we found, as I show here in this sort of 3D image of the cluster, we have here the red and green dots are cluster members from the main cluster in red and a background structure in green. And the blue boxes correspond to the galaxies that we detected in H1. So these are H1 gas-rich galaxies. And the three axes are right ascension, declination, and the third axis is essentially redshift, which is not really a distance, but a velocity. But you can see here that most of the H1 emission is really outside the cluster core, where we don't detect essentially any gas at all. So one thing that we did a few years back when I arrived in Chile was we tried to look at this from a different perspective. We wanted to understand the time scale of stripping. So we used phase-based diagrams. So for those of you that are not familiar with this kind of diagram, I'm going to quickly explain how they work. So on the x-axis, we plot for each galaxy the distance from the cluster center. And on the y-axis, we plot the relative peculiar velocity of each galaxy relative to the mean velocity of the cluster. Okay, so galaxies, the most massive galaxy in the cluster that is at the center will essentially be at 0, 0 in this plot. And if you plot all the cluster galaxies of one big massive, regular cluster in this plot, you will see something that looks like what I have here in this cartoon. Okay, you will have galaxies following this trumpet shape that is delimited by the escape velocity of this halo. And if we were to look at the trajectory of a galaxy falling in for the first time into the cluster, we will see something like what I plot here in this red arrow. This is exaggerated for just explaining what I want to explain, but essentially what you have is that you have a galaxy falling into the cluster, being attracted by the gravitational pull, being accelerated, so you gain velocity as you pass pericenter. So this is, I don't know if you can see my mouse, but it's at this first arrow here at the top. And then as you pass pericenter, you go to the other side of the cluster, deaccelerate, and then you fall back and keep falling back. And each time you fall back into the cluster, you have less velocity, okay? And essentially, you start losing velocity because of a combination of dynamical friction and violent relaxation. So the end result is that we can use this kind of diagrams, if we have a lot of galaxies, in a statistical way to infer more or less the orbital histories of galaxies. So we can say that in different parts of phase space, most of the galaxies are falling in for the first time, or most of the galaxies have been in there for a very long time. It's what we call the virialized region, okay? And I say this that we can use it statistically because this kind of diagram suffers from projection effects, okay? When we observe galaxies in clusters, we observe projected distances and line of sight velocities. So these are just things that we have to live with observationally. But if we build a big enough sample and we use simulations as comparison to interpret our results, we can do this. And we've done this in different papers, but with the added information of when ram pressure stripping hits the galaxies. So what we did was we took this analytic prescription of ram pressure stripping by gun and gut, and we put it into dark matter halos from a cosmological simulation to try to infer where in phase space this stripping can occur. And because stripping depends, as I said before, on the density of the intercluster medium and the velocity of the galaxy, these two parameters are essentially the x and y axis in this plot, because the density increases with shorter distances from the cluster and the velocity increases vertically in this direction. So stripping in phase space will be most efficient, more or less, in this roughly triangular region, okay? This depends on specific clusters and specific galaxies, but just to roughly show you how it works. So we put this very simple model into cosmological simulations, and we predicted for a given cluster, a given H1 detection limit, where we expect stripping to be visible. Okay, so here on the left, we show these results, this phase space map of the probability of a given galaxy of having been stripped enough to not be detected in H1. Okay, and on the right, I show you the observations that were matched to the simulations for the comparison, which come from this body survey that I showed you earlier. And on the right, you have that all the galaxies in the cluster are circles, and the H1 detected, so the gas-rich galaxies, have blue boxes around them. And you see that from the simulations to the observations, there is a very good match between both of them. What we learned from this experiment, it was quite exciting, because we realized that phase space diagrams were actually very useful, not only to trace, old and young populations in clusters, but to trace this cluster processes like ram pressure stripping. And in particular, this process is very fast. It seems to affect galaxies on first passage, so we can very clearly see it in phase space. And we learned that indeed there is a significant amount of gas loss in galaxies on first infall alone. So we start putting constraints to how efficient and how fast this process is. And we've been doing many other checks with this kind of analysis since then. Here I show an example. We went back to the Virgo cluster, so with Adi Chung and her student, Hein Yoon. And we looked, okay, let's do this same phase space experiment, but in the nearby universe, where we can actually see much better the morphologies of these galaxies in H1. And we actually saw that this picture that we had in mind is true, where, where outside the cluster, at large distances from the cluster center, we found these beautiful extended H1 disks, where it's the, I cannot use my mouse, so I just have to talk you through the slide. So at the top, in the blue box, you have this population of, I show 4 examples of galaxies that have these very extended disks. So we essentially divided all the H1 detections into 3 types. So the very extended disks, the tailed galaxies in radio, and the truncated profiles. And we mapped them in phase space and found that they actually correspond very well with the orbits within the cluster and what we expect from ram pressure. So first you have the extended disk, then as you approach the cluster center, these disks are stripped and you get these beautiful tails of stripped gas. Then this gas is lost and you leave the galaxy with this truncated gas disk profiles. And the galaxies are already starting to be quenched. So because at the outer parts of the disk, they don't have any gas to form new stars. So far I've been talking a lot about gas and radio observations, but as I showed from the simulations, we know that many times when you strip the gas, you can even form stars in these stripped tails. And in the literature, there had been many claims or discoveries of these so-called jellyfish galaxies that in optical and UV images show very long tails of UV bright material, so star-forming material. But it wasn't until 2006 that two big papers came out showing a significant large catalog of this kind of objects, okay? Because in the past it was, a couple of galaxies here and a couple of galaxies there, but there wasn't a systematic study of this kind of galaxy populations. So one of the two papers that came out that year was by our own collaboration. So Pojanti et al. 2016 published a catalog of over 400 of these jellyfish candidates in the nearby universe. So this comes from the WINGS and Omega WINGS cluster surveys at redshift of about 0.05, so quite nearby. And this sample was very precious because we could study for the first time these jellyfish galaxies as a population and try to understand what are the conditions that form these beautiful star-forming tails of stripped gas. So we proposed for a large MUSE program. So MUSE is an integral field spectrograph mounted on the VLT. It actually has 24 integral field units. It's a precious monster, as you can see down there, and now it even have adaptive optic capabilities. And what the integral field unit can do is that essentially instead of getting an image or a spectra for a galaxy, you get a data cube that consists of 90,000 spectra across 1 by 1 arc minute of the galaxy. So this is really a state-of-the-art instrument that is very helpful for this kind of studies. So we obtained MUSE data for 114 of these jellyfish candidates and a few control sample galaxies. And just to note that these galaxies, as I said, are nearby at redshift between 0.04 and 0.07 and have stellar masses from 10 to the 9 to 10 to the 11-ish, okay? And they span a broad range of environments. They're not all in one cluster. They are in many different clusters of many different masses and dynamical stages. So the PI for this survey is Bianca Pojanti, again, in INAF in Padova. And here I'm going to show you the first 50 galaxies observed by GASP. So because we have the MUSE data cubes, we can essentially reconstruct RGB images of how these galaxies would look if we just observe them with broadband filters, because this is how we selected them. So these galaxies were selected from optical broadband imaging. And you can see that, yes, we see some evidence of tails in these galaxies from these RGB images, but nothing extremely spectacular and nothing too obvious. But when we look at these galaxies only in the wavelength range of H-alpha emission, so ionized gas, we see a dramatic change, with many of these galaxies showing extended, very large tails of stripped gas. So I'm going to blink between the optical broadband images and the H-alpha for you to maybe, hopefully, compare some of these galaxies. So there's many things that you can do with MUSE. I'm going to showcase here one of them. This is cheating. This is one of the most spectacular galaxies in the whole survey, so because it has such long and beautiful tails. So here I show the two MUSE pointings. Most galaxies needed only one pointing, but because this one had such long tails, we put two MUSE pointings, and the results from the MUSE data is shown on the top, where the stellar distribution, the stellar continuum is in white and the H-alpha emission in pink. So you see that the stars, as I said before, are largely unaffected, but the gas is completely disturbed. And this galaxy is entering this cluster, kind of not directly falling towards the BCG, but it's definitely on first infall. And from the MUSE data, we can do a bunch of things. I don't want to bore you with the details, but we can look at the kinematics of the gas and the stars. Here on the top right, I show you the velocity and velocity dispersion of the gas in the tails, and you can see that the rotation in the disk is preserved out into the tail, so it's stripped, but it keeps a little bit of the rotation. We can look also using line ratio diagrams at what are the ionization mechanisms for the gas through BPT diagrams, and we can map for each spaxel in the cubes which places of the galaxy are being ionized by star formation, for example, which are the red pixels, or AGN, for example, which is at the center of the galaxy. We can look at metallicity gradient, ionization parameters, many things. But although we've done a lot of work on individual galaxies, trying to understand their properties, I thought it would be more interesting for you to hear a bit about the more kind of general results, looking at a large population of these galaxies, which we're starting to do now that we have all the data set completed. So we have a variety of jellyfish from the GASP survey. One of the first things that I was interested in doing was doing similar things of what we did with H1. So classify these galaxies according to how much stripped they are, if they just have a little bit of extended emission but asymmetric to one side, if they had this very long tails, we call them peak stripping or extreme stripping. And then we have these truncated profiles, which we call post-stripping. And of course, we also have a lot of galaxies that we have no idea what's going on. They have weird morphologies, and there's not a clear direction of an interaction. It could be merger, it could be around pressure, it could be harassment, it could be thermal evaporation, or anything. And we, of course, put all these different kinds of jellyfish galaxies in phase space, similar to what we did in UNETAL. And we found the same picture of incremental stripping as galaxies approach pericenter. So here in this phase space diagram, you have the blue stars are galaxies that are started to be stripping. Then the green stars that are mostly at the cluster center and at very high velocities are the cases of extreme stripping with very large tails. And then the orange stars are these unknown ones, and the blue ones, the ones that have truncated disks that we think that have already been through pericenter and then are backsplashing back into the cluster. So one of the things that we noted was that in general, if you look at just the velocity distribution of the jellyfish galaxies compared to the overall cluster population, jellyfish galaxies travel much faster in the cluster core than any other kind of galaxy in the cluster. Okay, so they're coming into the cluster very fast, as shown here on the right. So I'm plotting the line of sight velocity dispersion of the jellyfish galaxy population and comparing it with the star-forming galaxies, the passive galaxies, post-orbit galaxies, other populations within the cluster. And you see that jellyfish galaxies have this extreme line of sight velocities and dispersion. And this means essentially that, first of all, jellyfish are definitely on first passage through the cluster, because as I said, the more time they spend in the cluster, the more they lose velocity. And they prefer these radial orbits that go very fast, very near the cluster core. This makes sense because these are the perfect conditions to have intense run pressure stripping. And something that we're very interested in studying as well, just related to the orbits of jellyfish galaxies in clusters, is looking at the tail directions. Because the tail directions can also yield information on, the orbits of the galaxies. And here on the left, I show an example from a paper by Roberts et al. Last year, where they looked at the jellyfish galaxy tails in the Coma cluster, which is a massive cluster nearby. And they found that most of the tails of jellyfish galaxies point away from the cluster center. And on the bottom, you have a histogram of the angle of these tails. And indeed, you see that, the distribution is very skewed towards large angles, or 180, which is when the tail points exactly away from the cluster center. So this fits in very well with the idea that the strip tails are mostly visible during first passage through the ICM, and then we're not going to see the galaxies as jellyfish anymore. And we're doing some kind of statistical work to constrain the exact timescale of this. And I'm just gonna, if I have time, I'm gonna just give you some highlights, some general highlights from the GASP collaboration in the last years. So I'll start by perhaps the most unexpected and one of the most exciting results from the collaboration, which is that we found a previously unknown connection between ramp pressure stripping and AGN activity. So the mechanism that feeds the supermassive black hole in the center of galaxies. And we found this because when GASP was still ongoing, we hadn't finished, we had observed 7 of these most stripped galaxies, the ones with very large tails. And we saw that 6 out of 7 of them had an AGN. This was based on emission line diagnostics and also X-ray information. And this fraction, 7 out of 7, is a very high fraction when you consider that AGN are a pretty rare population. So if you look at cluster galaxies or field galaxies, the fraction of AGN in general is no bigger than 10%, let's say. So we thought, maybe this is a strong indication that perhaps AGN is helping somehow ramp pressure or the other way around. So to understand which was helping which, we looked again at my favorite plot, the phase space diagram. And we found that the jellyfish galaxies with AGN were all within this region of phase space where we expect stripping to already be very intense. So we concluded that intense ramp pressure stripping somehow is helping not only to remove gas from the disk of the galaxies, but to funnel gas inside the galaxy center and trigger the feeding of this massive, supermassive black hole. And there is supporting evidence for this scenario from other works, observational and also simulations, that say that somehow the gas could be being funneled towards the center. What else have we learned? So when we look at kind of the details in these galaxies, we can see a lot about how star formation is happening or being truncated in the galaxies. So this is one of the textbook jellyfish in our survey, JO201. It's a dear galaxy to me because it was the first one we observed in a pilot study. So I've looked at this galaxy a lot. And it's beautiful because it really clearly shows the 2 kind of main things that can happen in this kind of galaxies. So one thing, well, more than 2 things, but I'm just going to highlight 2. One of the things is this leading edge. So we think that the right-hand side of this galaxy is the one interacting with the intercluster medium. So in this side of the galaxy, the gas is being compressed. And star formation is triggered in this shock front, if you want to call it, or leading edge. And on the opposite side of this edge, we have these beautiful strip tails, okay? In this image, you have a combination of near UV observations from the AstroSat Indian satellite, H alpha from the MUSE observations, and O3 emission also from the MUSE observations. And you see clearly O3 dominating there in the center where we have an AGN. And in the tails, we have 2 things happening. We see many knots where star formation is occurring in situ, in these clumps of star formation. And the mass distribution of these clumps is actually pretty comparable to ultra-compact dwarfs and globular clusters. So this could be one mechanism to form these objects outside of galaxies. And we have another component that is not in these clumps, but it's a diffuse component ionized by a combination of star formation and composite liner-like emission, okay? That it's a component that is perhaps interacting more closely with the intercluster medium. And in the disk of the galaxy, if we integrate over the whole stellar disk of the galaxy, we see a moderate but significant enhancement of the star formation rate at all masses when we compare with a control sample of non-stripped spiral galaxies. So this is what is shown here by Benedetta Vulcani in one of her many gas papers, where she shows the comparison sample in black, the black dots and line, and the jellyfish galaxies in color. And the blue line is a little bit above significantly, with a significance compared to this control sample. So we think that RAM pressure stripping eventually quenches the galaxies, but these galaxies can go through a temporal period of enhanced star formation. And if we want to look at kind of the spatially resolved version of what is going on in these galaxies, here I show you 3 key regions of one of these jellyfish galaxies. So as I said, we have these star-forming clumps, and if you look at the spectra, you have this very nice, normal emission line spectra. If we go to the galaxy center, we have emission that is very broadened and dominated by the AGN. And in this particular galaxy, I like to show it here because at the edge of the stellar disk, where you've already stripped the gas, if you look at the spectra, you already see signs of post-starburst features. So you have this, this kind of spectra that I show here that tells you essentially that the star formation history in this region was that you had a burst of star formation and then you start quenching the galaxy. So this is what we think is going to happen across the galaxy, just from the outside towards the central parts. And a confirmation for this, and I'm going to try to speed up here. A confirmation for this comes also by looking at metallicity gradients that also showed us that quenching happens from outside in, because the most stripped parts of the galaxy have the lowest metallicities. And I'm just going to show perhaps one more result. I'm going to jump through some of them because I want to keep inside the time. This is an exciting result by Ankla Muller et al. 2020. I'm not even in this paper, but I think it's wonderful. She showed, so she looked at polarization using JVLA in one of these galaxies and found extremely highly ordered magnetic field lines that go along the strip tails, parallel to the stripping direction, okay? And these are large-scale magnetic fields with a very high fraction of polarization and steep radial spectral index. And basically, the conclusion from her study that also compared the observation with high-resolution simulations is that the magnetized plasma from the intercluster medium condenses into the external layers of the tail, and then it's compressed and sheared. And essentially, this magnetic field, this very collimated magnetic field, is shielding the star formation and allowing it to happen for longer times. So basically, what the simulation shows is that if you did not have magnetic fields, it would be much harder to see these long tails of star-forming knots. Okay, so magnetic fields, I think it's a kind of a new window we need to really explore to understand a lot better the details of these interactions. And I'm gonna just show my conclusion since I think time is up. I hope I've convinced you that RAM pressure stripping is a very effective mechanism removing gas from galaxies in clusters. It's a very fast mechanism that can affect galaxies even in their first passage through the cluster. And that these jellyfish galaxies are very interesting because they trace cosmic migrations. They're basically migrants that go from low-density regions to these clusters of galaxies, and they're galaxies that just arrived to that environment, so they are transformed radically in their first stay in that new environment. And we've learned a lot of things, especially with the GASP survey, of how gas is removed outside in, and also quenching will happen in that order. You can have star formation enhanced in the disk in one moment. You can feed the black hole when RAM pressure stripping is very intense. And I didn't show it, but you can also unwind the spiral arms of galaxies with ramp pressure winds. We can have in situ star formation forming outside the galaxies and tails, where you also have ordered magnetic fields and a very complex interaction with the intercluster medium. So I hope that you have lots of questions. I'm just going to finish with a key advertisement for a postdoc position that we have here in Valparaiso opened. If anybody's interested, please contact me. All the details are in AAS job register, and the deadline is the end of March. So thank you very much. I'll leave my final slide and I'll take questions. Oh no, I think I have to stop sharing to see it.
Thank you very much. So I'm gonna show you the question and read them out loud. So Thiago, that's a professor at Valongo, say, hi Yara, great talk and amazing data. Can you talk a bit more about the BPT diagrams? Can you trace the shocks using line ratios as well?
Yes. So for the BPT diagrams, we make different BPT diagrams using different kinds of lines. And in particular for the AGN sample, there is a paper by Mario Radovic, where we tried to use finer modeling to separate the contribution from shocks and AGN in the AGN sample. We wanted to know how much real AGN that emission was and how much it could come from shocks. And he found that it was mostly AGN. Now, in the tails of galaxies, we also see some shocked regions, for example, from O1 emission, that we're trying to link with different wavelengths. I don't know if I had a slide for that I jumped. Yeah, so for example, in the X-rays, I'm not showing you my screen, sorry. I'll be very quick.
No problem. We have plenty of time.
Okay, good. I just hate going over time. Okay, so this is a multi-phase view of one of the galaxies in many different wavelengths. And in particular, I want you to look at the bottom left, where we have X-ray information. And in this X-ray tail, in this position of the X-ray tail, we also have an excess of O1 emission and a lack of star formation. So we think that shocks could be one of the players creating these conditions, for example, okay? So where you don't have star formation, but you have other tracers like X-rays or O1, it's an indicator of that. I don't know if that's what you wanted to hear.
I think so. So next question is from Karin, also professor in Valongo. Says, hi Yara, in the stripping class in GASP with asymmetries, one could have contamination from mergers. You mentioned this. Can't you eliminate the merger possibility by looking for companions?
Hola, Karin. So I would say that the GASP sample, so I didn't go into the details of the sample I showed today was only in clusters. GASP has also a sample outside of clusters, and you can read Benedetta Vulcani's papers on this. She has done a lot of work on the non-cluster sample, and in the non-cluster sample, you have some mergers. And with the MUSE data, you clearly see it because you see the interaction in the kinematics, etc. In the cluster sample, we have essentially negligible contribution from mergers. And we know this because with MUSE data, if there is any kind of other blob or companion within the MUSE field of view, we immediately get a redshift and we get all the kind of interaction within these different galaxies. So we can discard that. And the other thing is that, well, when you look at only optical images, broadband images, you don't have all this information. And that's why in the Poyanti 16 paper, we call them jellyfish candidates, because you don't really You don't have a 100% certainty that this is just run pressure stripping. With the MUSE data, you can see how the gas and the stars behave differently, and that already gives you a strong indication that it's a hydrodynamical interaction. So negligible contribution from mergers for the sample I showed.
Okay, so another question from Thiago that says the result from the tail direction is very interesting. So is it expected from simulations that galaxies lose their gas before first passage through pericenter?
So I think the answer is not one answer. It depends. It depends on the galaxy mass, the ratio between the galaxy mass and the cluster mass, the dynamical state of the cluster, and the orbit of the galaxy, and also the inclination. There's a lot of things to consider, but we're trying to constrain this using large. The main problem, the main limitation we have in order to constrain this is that we need very large samples. And in all these samples that I mentioned in the literature, the largest catalog is the Pojanti one, and this is 400 galaxies, and in clusters, less than half. So this is, to do a statistically robust quantification of this, we need more galaxies. But we're working on it. There is a postdoc working with me here in Valparaiso that is trying to build, kind of compile everything we know and look for new ways of finding these galaxies in kind of large surveys. And hopefully there we can answer these questions better.
Okay, then there is a question from Yana, a student in Valongo. She say, really nice work, Yara, thank you. Sorry if I miss it, but how do you differentiate post-stripped system from those unsure? Because by the figures, they looked very similar.
Okay, so post-stripped are essentially galaxies. I think I didn't, sorry, I think I didn't explain what the colors were. Let me go back. Okay, so here the red contours, I'm very sorry, I didn't mention it. The red contours are the stellar body of the galaxy. And the yellow-blue color bar is H alpha. Okay, so if you compare the H alpha with the stellar body in the post-stripping case, you see that the galaxy only has gas at the very center. It's been truncated, okay? While in the question mark unknown, the gas is covering all the stellar disk, but it has this kind of tails or asymmetries in three different directions. So here you have in this direction, and in this direction. So we really don't know what's going on. While in here, you have one sort of tail coming only from the central part, and all the external parts of the disk have been stripped. So that's the main difference. I don't know if you could see my mouse when I was moving it.
Is that the figure are tiny somehow? It's a bit difficult to see the red circles.
Yeah.
For me, but maybe Yana can start.
No, I'm sorry, and I didn't even mention them, so my bad.
But we can check. We'll check your paper. So we see. Okay, then there is another question from Karim asking, in the simulated phase space diagram, a tail of galaxies with a high percentage of being stripped coincides with the region of virialized galaxies. Is it that these are stripped in their second, third passage?
In the simulated phase space diagram, which one would that be? A tail of galaxies with a high percentage coincides with the region of... Okay, I'm gonna go back to that plot. I think Karin means the bodies comparison. This one, I think. I'm gonna... If I got it wrong, can you see my screen?
No.
Oh, okay, sorry. Share.
And you can keep it there because I can include it and exclude it. Oh,
Okay. Okay, so I think Karin asks, there is a tail of galaxies in the virialized region. So in this particular cluster, there is maybe a couple of H1 detections in this virialized region. Here I have to first make a big caveat that the fact that we see one galaxy there doesn't mean that it couldn't be. I mean, this is a lower limit to the real distance from the cluster center, because we're looking at projected distances. So maybe if we did this in 3D, it would be much further out. In fact, we expected a bit more contamination in this region than we see. It was a kind of lucky cluster that we see it so clean. But it could be that this is just projected and it hasn't gone through the cluster core yet, or that it wasn't stripped enough, that in its orbit it didn't reach a point of too intense run pressure and it wasn't stripped enough. In this particular case, we don't have tail directions. So when we put in the information of tail directions, we can know much better for each galaxy what's the situation. But it's something that we have only done for like one galaxy here, one galaxy there, but not for the entire sample in a coherent way. But we're working on that with Rory Smith in Korea.
okay, that's great. And I look. Okay, and then we have a question from Denise, a professor in Valongo, that says, first of all, thanks Yara for this very clear talk, even for not expert in the field. And then she's asking, could you please repeat the result about the metallicity of this kind of galaxies? This metallicity gradient is the result for one particular target, or is that for a sample?
Okay, thank you for the question. I rushed this a little bit. So if you look at normal galaxies, not stripped, not jellyfish, these galaxies, you will find that the metallicity gradient goes from higher metallicity in the center and lower metallicity in the outer disk. Now, if you imagine that somehow you're stripping the outer part first, you expect the tails to have lower metallicity in the gas phase metallicity, okay? And this is what we see here. In fact, for this galaxy, we have this kind of purple, deep purple dots trace a spiral arm that was actually broadened. I didn't have time to talk about that, but the stripping sometimes, what it does is that it takes the spiral arms and it opens them, it broadens them. Since you asked, I'm going to show this slide that I skipped here. So this is a paper by Callum Bellhouse. And here he compared the observed stripped gas from gas with simulations, both in the case of face-on stripping, when the galaxy is falling face-on towards the cluster, and when it's coming sideways, edge-on. And in both cases, the simulations show that you can unwind or broaden the gaseous spiral structure of these disks. And if you have certain metallicity in one of these spiral arms, as you push it away, you will detect this kind of structure with the same metallicity in the stripped tail. And there is a paper by Andrea Franchetto last year where he analyzes all the metallicity gradients in the gas galaxies. If you're interested in this, there is a reference.
Okay, thank you. So then we have a question. Is the last question from Marco Grossi, a visiting professor in Valongo. Is asking, saying, very nice talk. Can you comment a bit more on the run pressure stripping effect on the molecular gas component in your sample? Thank you.
Thank you, because I didn't have time. So there are some nice papers on gas not written by me, but by excellent people, including Alessia Moretti, where they looked at, well, some people have looked at H1 and some people have looked at molecular gas. And in particular, the molecular gas is super interesting because in gas, we're finding that CO, so molecular CO gas, is overabundant in these stripped galaxies by a factor of almost 10 compared to non-stripped spirals. Okay, so we think, so if you combine the total amount of gas available for star formation, so neutral and molecular, the amount is similar, but somehow the ratio is not. So we think that there is a very efficient conversion of gas from neutral to molecular in this kind of environments. And yes, we don't have molecular gas observations for galaxies, only a handful with ALMA, but I think the results are very exciting. And also the molecular gas observations have helped us understand that star formation does happen in situ outside the galaxies in these tails.
Perfect. Okay, and then Luan also thanks you and agree with Denise that it was a very nice and explanatory talk. Yana, thanks. And Karin confirmed that it was the correct plot, the one you showed.
Good.
And Mariana as well, thanking you for the great talk. We get the final question from Karin again. Isn't it that the neutral gas is stripped first? I think Marco has some work on this on dwarf galaxies.
Yes, the neutral gas is definitely stripped first. So because the neutral gas is much more extended than the molecular gas. So you strip the neutral gas, but we think that a lot of the molecular gas that we see in the tails of these jellyfish galaxies is formed from the stripped neutral gas, okay? But yeah, what you strip is mostly the neutral gas, indeed.
We have a final, just appeared question from Douglas that is also working in Valongo and help us organizing the seminar. And he's saying thanks you for the talk. So can the RPS cause morphology transformation on the opening of the arms? Are specific cases?
So I'm assuming it's Rampressor stripping, what he means by the, okay.
Yes, it is here.
Okay, so that's a very good question. The morphology of the galaxy, when we think of morphologies of galaxies, we generally think of the stellar light from these galaxies. It depends on which wavelength, essentially, you define morphology. This broadening of the spiral arms is something that we see from the gas, so from the stripped gas and the star that could be formed from this stripped gas, but not the bulk of the stellar mass of the galaxy. The bulk of the stellar mass of the galaxy will remain unperturbed because it's not going to interact in that way. However, when you enter a cluster, you not only feel Rampressor stripping, but you feel harassment, you interact with the whole gravitational potential of the cluster. You have many other things going on. And I think one problem of being very focused, like in the community, typically, okay, I work on mergers, I work on AGN, I work on Rampressor, but all of these things happen in combination, right? So I would dare speculating that Rampressor stripping is helping to quench these galaxies. So it's removing the star formation. It will wash out the spiral structure because that comes from the gas component. And then the thickening of the disk and the bulge will happen through other additional mechanisms, okay? So, for example, if it's true that we funnel gas towards the center and we feed the black hole, and maybe we increase the star formation, we can bulk up the bulge. Maybe through harassment, we can help thickening the disk somehow. But I think we need to kind of put this into a bigger context of what other things can happen to the galaxy. But the ramp pressure is definitely a gas effect that can form stars outside. But I wouldn't dare saying that ramp pressure stripping alone is transforming the overall morphology of the galaxy. I think you need other things happening too.
Very nice. Very interesting thought that the galaxy morphology is wavelength dependent.
You know more about that.
So Karin saying that it's such an interesting subject that we don't want to stop asking questions. And with this, we thank you a lot again for the talk. We are perfect on time. You've been fantastic.
Thank you so much.
We hope to see you in Rio.
Yes, thank you so much. I really hope to meet Valongo one day in the near future.
Okay, so ciao, Yara. You can stay. I just and yes, let's see you all in the next talk.